Okay. So first off, do you guys have any questions from 3.1? Right? There was a video I made you guys watch from a previous class on it. If you have a question, please ask me now before we get going into 3.2. Weird. Okay. Hold on. I'm going to save this too. For some reason, it's not going to YouTube, so I'm going to record this as well. Okay. So let's get started. 3.2. Now, 3.1 was over the quadratic, which is a very specific type of polynomial. 3.2 now talks about a broad definition of polynomials. We're going to talk about polynomials. We're going to talk about their end behavior. We're going to talk about multiplicity actually at one point, and then we're going to finally get to finding zeros, which is what chapter 3 is all about. Really, chapter 3 is all about. It's kind of a keystone concept for college algebra. So before we get there, let's define what a polynomial is. So polynomial turns out to be, by your book's definition, just a string of terms where the coefficient has to be a real number and the variable in the term is the domain variable, and it's always raised to an integer greater than or equal to 0. So let me give you, I'm going to kind of go over that with examples. You can read the definition. It's on page 348. But if we had something like f of x equals 2x to the fourth minus 8x squared plus 4x minus 1, okay? This is a really solid example of a polynomial. Now, if you look at each one of these terms, there's 4 terms here, right? The coefficients 2, -8, 4, and -1 are all real numbers. There's no I values, right? And the x values are all raised to an integer greater than 0. So now I do want to show you this one thing. So notice this is considered the leading term because it's the largest exponent. And there's our degree right there. So notice it's raised to the 4th power. It's not 4.5. It's not 1/2. It's not 2/3. It can't be a fraction. It has to be a nice whole number. So 4, 2, really this is 1. Now constants actually have an x. It's just not written because it's x to the 0 power, okay? And notice we got 4, 2, 1, 0. Anything raised to the 0, remember it's just 1, so we don't write it. But know that there's a variable there. It's just that we don't write it. It's just x to the 0. Now notice these are in descending order. Now, in the next section, we're going to talk about descending order with missing terms. There's a missing term here, the x cubed term. So I'm going to write this just for now. You don't have to do this, but this is, if I wanted to write this polynomial in descending order with missing term, which we're going to need to know for 3.3, you would have to put an x cubed variable in there. So we would say 2x to the 4th plus 0x cubed minus 8x squared plus 4x minus 1. Because we don't have an x cubed variable, we would have a missing term of x cubed. Now, we don't need that for this section. I'm not worried about that, but it's going to pop up in 3.3. So I wanted to go over it because of that. Okay, but anyway, this is a good example of a polynomial that right here, we'll call this one 1. Now, something that wouldn't be a polynomial. Let's say we've got g of x, and I'm going to do a few different reasons why it wouldn't be a polynomial. Let's say we have 1/2 square root of x minus 1 over x plus something else. I won't do the I. That's a little too easy. Let's just say plus 4. Now, there's really 2 reasons why this is not a variable. The first is because if we look at this first term here, the square root of x, remember the square root is raising something to raising to a 1/2. So if I rewrote this as an exponent, this would be 1/2 x to the 1/2. And we cannot have anything raised to the 1/2 power. Okay, it has to be nice integer numbers. 4, 2, 1, 0, 3. Okay, can't have the 1/2. That means this is not a polynomial. In the second term, remember, if x is in the denominator, if we want to write it in the numerator, we would have to raise it to the negative power. Well, if it's x to the 1 in the denominator, it's really x to the negative 1 in the numerator. Well, this also is an indicator that this is not a polynomial because we have a negative exponent on the x. So can't have negative exponent, cannot have fractional exponent. This is not a polynomial. Right, polynomial, many, nomials, right, many, 4, there's 4 here, nomials. Okay, so that's where it comes from. Now, why is it important that we have polynomials? Well, if we have polynomials, we actually have smooth and continuous graphs, okay? So polynomials produce smooth and continuous graphs, okay? They're going to be smooth. There's not going to be holes like we saw in the last last test. There's not going to be vertical asymptotes like we saw in the last test, right? We're going to have not actually. Was that? No, that was the other class. I'm sorry, guys. That wasn't you guys. We'll get to that actually in 3.5. But we're not going to see anything goofy on the graph. It's just going to be smooth and continuous. Here, let me show you what I'm talking about. I'll give you an example, kind of some graphs that are polynomials and some that aren't, okay? Just visually what's going on. Like that quadratic that we graphed a lot in the last section, it is a nice polynomial. It's a second degree polynomial, right? It goes up, but notice it goes forever to the left, forever to the right, and it's just nice and smooth. Continuous means it goes forever to the left and forever to the right. It means that the domain's all real numbers. So when you hear the word continuous, it really just means the domain is all real numbers. But forever to the left, forever to the right, just smooth. Okay, so another example of a nice polynomial graph would be maybe something like this. So, something like that would be a nice polynomial graph. Now it might be steeper, it might be flatter, but it's just nice, smooth, and continuous. Now, things that aren't would be graphs that like jump around. Let's say if we had something that we kind of saw these with the continuous or non. I'm trying to say in the increasing and decreasing section. If we had something like this, this is called a jump graph. Notice we go from here, we're coming along, and then we jump up to another section. So we've got a gap here in the graph. This is actually considered continuous, but it's not smooth though, because we have this jump. It's not continuous. I lied. Okay, time out. Rewind. This is not a continuous graph. Okay, not a continuous graph. And then if we had what I was talking about earlier, what's called a vertical asymptote, we're going to talk a lot about vertical asymptotes when we get to section 3.5. But a vertical asymptote looks like this, where it goes up forever that way. And really what you have is you have this vertical line that we just can't cross. So maybe something like this. So these two are good examples of not polynomials, okay? They're not continuous. And even you could have something like a corner graph. Oh, the absolute value graph. We've talked about that, right? It's not a polynomial because it has a corner to it, okay? See, if it has something like a corner, again, not a polynomial. So these are good examples of non-polynomial graphs. These two are perfect examples of polynomial graphs, okay? Nice, smooth, and continuous graphs. Any questions about that, Brianna, Amanda? Let me know. Just stop me if I'm getting a little too crazy. This isn't that deep. It's just that it's going to lay a foundation for polynomials, which we're going to be talking about over the next 3 sections, okay? Okay, now, there's 2 ways to write polynomials. I kind of go about this in a little different order than your book because I think this next part's really more important. There's 2 ways to write polynomials, actually. There's that way we just talked about. Let's say f of x equals, 3x to the 4th minus 2x cubed plus x squared plus x minus 1. Okay, This is, I'm going to call this the non-factored form, okay? This is a non-factored form. And then another way to write a polynomial is in factored form. And it's really nice when these are actually written in factored form. So I'm going to write it as like, let's say x minus 4 times x plus 2 times x minus 1 times x plus 3, okay? This would be factored form. And notice we have factors all along the way. And this we have we have terms along the way. There's nothing wrong with writing a polynomial in both of these ways, I guess you can say. They tell us a lot. What am I trying to say? There's pros and cons in both ways. That's kind of the best way to put it. And I'm going to go over these here in a second. And actually, I'm going to start by doing this with kind of a more basic example to show you what's going on, because the first thing we're going to really talk about in this section is the end behavior of these polynomials. And for the end behavior of a polynomial, we have to have the leading term, okay? We have to have the leading term. So I'm going to start, actually, I'm going to kind of pause this. I'm going to start with a factored polynomial. I'm going to say h of x. 2x plus 1 times x minus 3 times x plus 4, okay? And now look, if I wanted to, now you don't have to do this. I want you to show you, I'm just showing you how they connect to each other, how they relate to each other. But if you want to, you could multiply these out and wind up in the non-factored form, kind of the term form. So I'm going to do this. So if you wanted to multiply this out, you need to FOIL out this, or two of them, and then multiply in the other. So I'm going to focus on these first two over here, and let's FOIL this out. So you wind up with x squared plus 4x minus 3x minus 12. You got the 2x plus 1 out there, right? This is still h of x. And then I'm going to combine these two terms. So I get, that's just x squared plus x minus 12. And then I'm going to distribute each of these terms in. So you got to distribute the 1 all the way through and the 2 all the way through, okay? So if I distribute the 2x all the way through, I'd get 2x cubed. 2x times x, so that's 2x squared. 2x times negative 12, that's negative 24x. Distribute the 1, well, anything times 1 is itself. So I just multiply the 1 through, 1 times x squared, 1 times x, oh, that's not an x squared there. That's just an x. And then 1 times negative 12 is negative 12. Now I got to combine like terms. So 2x cubed. Now, I have a 2x squared and an x squared, so that's plus 3x squared. A negative 24x and an x, so that's minus 23x. And then lastly, a minus 12. Okay, I know that was a lot, and I kind of sped through it, but here's what I wanted to get to actually. Realize that these two polynomials are the exact same, just one is written in factored form, and one is written in this term form, okay? Kind of the standard form of a polynomial. And what matters for this next part that we're about to talk about is the leading term. Now notice, hold on, I'm going to sneak another piece of paper under here. So I keep going, okay? Notice in this factored form, it's easy to find the leading term. It's always, if it's written in descending order, it's always the term with the highest exponent, okay? So it's always the term to the left if you've written it in descending order. So the leading term is going to be 2x cubed. And what matters for us is actually the degree. Notice is 3. Okay, that's going to tell us something. And also the leading coefficient is 2. Okay, and really the fact that it's positive or negative is what's going to tell us. We'll get to that in a second. Now, if we go back up here, though, to the factored form, h of x equals 2x plus 1 times x minus 3 times x plus 4. Look, it's not as easy to see the leading term here in this factored form, but it's still easy to find, actually. So if you're given factored form and we need to pull out the end behavior, which we need the leading term for, and we'll get to that here in a second. I know I'm kind of getting the cart in front of the horse a little. The leading term is always just the highest degree term multiplied in each factor. So notice we have three factors. And the leading term for each factor is we have 2x, x, and x, okay? If we multiply those all together, 2x times x, we wind up with 2x cubed. Hey, same thing as before, okay? That's where it comes from. So if we're given factored form, we don't have to multiply it all the way out to get the leading term. We can just multiply the highest degree term in each factor, okay? And again, we know the degree is 3 here, and the leading coefficient is 2, okay? So I'm going to do a few of these, and we're going to just determine the leading term with the degree and the leading coefficient. So if I gave you an example here, and this is not hard, actually it's going to be a lot quicker than what we've been doing because now that we know how to do it actually. Let's say we put a term out front. Let's say we have 4x, let's do negative 4x. Negative 4x times x plus 1 times x minus 2, okay? Now, I need your brain to realize that this is a term out here, okay? And the main reason it's a term, or a factor, I should say, is because it has an x value, okay? Because it has an x value, that's going to be considered a factor. So we have three factors again. And if you want to write this in parentheses, it's fine. You can do that. But I need to multiply the entire negative 4x, the entire coefficient out front, by the x and by the other x. So my leading term is going to be negative 4x times x times x. Oh, that's going to be negative 4x cubed, okay? Now, again, my degree is 3, and my leading coefficient now is negative 4. Now, look, though, I need you to realize something, and it's kind of neat, and it's going to lead to a bigger thing here in a little bit. Notice we have three factors with x's, and our degree is 3. Three factors with x's, and our degree is 3. That is not a coincidence, okay? Not a coincidence at all. The number of factors with just an x variable will be our degree. Kind of cool. Kind of relates to each other. I know. It's fascinating. You guys can calm down on the other side of that screen. Okay, so let's do another one. I'm trying to throw some curveballs at you just so you can kind of see how these might look as we go along. So if we had, let's go back to f of x. Then we had negative 2 times x minus 3 squared times x plus 5, okay? Now listen, I need you to realize if you have a factor that's squared, what's really going on is we have 2 of these being multiplied. So you're more than welcome to rewrite it as negative 2. Actually, you know what? Let's add another factor here because we've done so many of these. So let's add x plus 1. Multiply, or not add, but multiply. X plus 1 at the end here. So negative 2 out here, and then we have x minus 3. And really what we have is x minus 3 times x minus 3. That's x minus 3 squared, okay? And x plus 5 and x plus 1. Okay, so if I asked you for the leading term, notice this negative 2 does not have an x, okay? It does not have an x. It's not considered a true factor. It's really just a coefficient. But when we find the leading term, we have to multiply it in. So we're going to multiply negative 2 times x, times x, times x, and times x. So negative 2 and then 1, 2, 3, 4 x's, so negative 2x to the 4th. And notice our degree is 4. Our leading coefficient is negative 2, okay? Degree is 4. Leading coefficient is negative 2. And notice 1, 2, 3, 4 factors that contain an x. That's not a coincidence. 4 factors that contain an x, and our degree winds up being 4. Okay. Questions? Okay, I'll tell you just a little hint, and we're going to get to this here in a minute. Because this x minus 3 is squared, that means it has a multiplicity. And we'll get to that in a minute, but your book uses this term multiplicity. And it's because it has multiple factors. Multiple of the same factor, I should put it that way. Multiple of the same factor means multiplicity. I'm going to define that more here in a little bit when we get there. But really, we're finally to the first real topic in the book, which is the end behavior. Of polynomials. In behavior of polynomials. So what is in behavior? Well, it turns out polynomials, they're always going to end to the right or left, going up or going down. Okay, so up or down. So when we graph a polynomial, like when we go back to over here, let's go back to this one. Remember, these were polynomials up here. They're always going to end going up or going down, and same thing to the left, going up or going down. You're not going to get any like flat lines, which we don't. Oh, kind of right here. This one, see how it kind of settles out right here? You're not going to get that with a regular polynomial. Okay, it's never going to flatline. It's always going to go up or down, left or right. And it turns out the degree and the leading coefficient tell us how it ends, how the graph ends. So we don't have to graph it per se to know. We can just look at and determine this from the leading term. Okay, and it's actually going to come from the degree and the leading coefficient. So let's see how that works. I'm going to do this one based off examples. Okay, so let's say I gave you f of x equals, let's do one we know already actually. Let's say we've got 3x squared minus x plus 1. Hey, this is a nice quadratic polynomial. And look, we know the end behavior here, right? Because the 3 is positive, we know that this is going to end going to the left up and to the right up. Okay, but I want to show you in polynomial terms why we know that. So the leading term is 3x squared. Now, what matters is if the degree is even or odd. So I'm going to make the rule here. The degree here is even, right? And then the leading coefficient is positive. I'm going to kind of make a quick sketch. I'll do it down here. Now, because the leading coefficient is positive, I know when our graph goes to the right, it's eventually going to go up, okay? It's going to go up because it's positive. Now, because it's even, I know it has to be symmetric around the other side. So I'm not going to define what's going on in between here, but I know to the left, it's also going to go up because with even, there's symmetry. You guys remember the even symmetry? It kind of comes from that, okay? Well, this graph is not even symmetric, but because it's even, it's going to come from the other side. Now look, shorthand, here's how we put this. So for end behavior, we would write it as to the right it goes up. Oh, shoot. The right it goes up and to the left it goes up. Whoop. From the right it goes up and to the left it goes up. So this is actually the end behavior. And we know that. I mean, it's a quadratic. It's smiling, right? So it's going to do, the graph's going to look something like that. So our end behavior is to the right. Since it's positive, it's going to go up and to the right. And since it's even, it's going to be the same on the left. Okay, so let's look at another one. If you've got a question, ask me as I'm writing these out. Let's say I've got negative 2 x plus 1 cubed times 3x plus 4. Okay. Now listen, this is in that factored form, right? Which is fine. We can still find the leading term and get the degree and leading coefficient from this. We've done this before already, right? So now look, this thing's cubed. I'm not going to write it 3 times. I'm just going to know when I multiply to find the leading term, I've got to multiply that 3 times, right? So for the leading term, I would multiply the negative 2 times x times x times x, and then times 3x. So negative 2 times 3, that's going to be negative 6. And I wind up with 4 x's, right? X to the cubed and then an x here. So my leading term winds up being negative 6, x to the 4th. So my degree, just like the example before, is going to be even, right? It's 4. But what matters is that it's even. But what's different is my leading coefficient. My leading coefficient, instead of being positive, my leading coefficient is negative. Okay? So what this tells me is that, look, because the leading coefficient's negative, as I go to the right, I'm going to wind up going down, okay? I'm going to wind up going down because it's negative. Now, because it's even, it has to be the same on the other side. So I'm not defining what's going on in between, but I do know from the left it's also going to go down, okay? So the way I would write this is to the right it falls and to the left it falls, okay? To the right it falls and to the left it falls. And
What
notice,
happens when you have an odd?
wait, Tom, I can barely hear you. Hold on, let me make, oh, can you just talk a little louder? My speaker's really.
What happens when you have a degree that's an odd?
Oh, we're about to get there. Hang
Okay.
tight, Amanda, or Janie. I'm not sure who said that.
Amanda.
Okay, yeah, hang tight, Amanda. That's the next thing. Okay. But no, okay, I'll tell you though. Let's kind of make an assumption from this. If even means they're the same, odd's going to mean they're opposite. Okay. But any other questions before I go to the next example? Okay, good. Let's look at one of them. Let's look at another one. Let's say I've got h of x, and it's x cubed minus x squared plus 4. Okay. And again, it's nice when it's written in these terms to get the end behavior. I'll tell you, when we get to solving, it's a lot easier if it's already factored when we're solving. But it is nice in these terms whenever to get the leading coefficient to really get the end behavior. Leading term, I should say. So our leading term is x cubed. So what matters, our degree is odd now, right? But our leading coefficient is a positive 1, right? So it's positive. So yeah, what does this mean? Look, our leading coefficient being positive means we're ending up going up and to the right, okay? Just like before, just like this one we had earlier, right? Because we have an even or a positive leading coefficient, we're going to wind up going up and to the right. It's because when we put huge numbers in, this degree takes over. And because that leading coefficient is positive, it's just going to be positive. Okay, so we're going to go up and to the right. Well, the difference though is it's odd. So instead of being symmetric around and going up, it's going to go down. So I'm not defining what we're doing here, but I know it's going to be opposite on the other side. So the leading or the end behavior is going to be falls to the left, rises to the right. Okay, falls to the left, rises to the right. So if it's positive, we know positive means it goes up and to the right. It's odd, so it's going to go down and to the left. Okay, so let's do one that's factored now. Let's say we got z of x, and let's say we have negative 2x times x plus 3 times 4x minus 1. So wait, yeah, that'll work, right? If I asked you for the leading term here, look, this one has an x. I mean, we've got to multiply it either way. We'd have to multiply it, but notice we have 3 x's. So negative 2x times x times 4x, so it's going to be negative 8x cubed. So the degree is odd. And this time the leading coefficient is negative. So because that leading coefficient is negative, it has to wind up going down, okay? As the x's get larger, it's going to wind up going in the negative direction, okay? But it's odd, so this one's going to go up on the other side. So stuff happens in between, but we know to the left it's going up and to the right it's going down. So this would be our end behavior. Rises to the left, falls to the right. And your book uses like some language, and even on the test, the language sounds like that. For some of the questions, it'll say, like for this one, I'll ask, oh, what's the end behavior of this graph? You'll have to say, oh, it falls to the right and it rises to the left. So don't get caught off guard. You might just have to kind of read it, interpret it a little. But falls to the right, rises to the left. Okay. Questions now. Look, I'm going to go on from this, but realize I'm going to ask questions about it as we go to the next topic. This is always just a good question to add, like, hey, what's the behavior? And we'll go over it. We'll get a lot of repetition as we go over the next few sections on the in behavior. Okay, so let's talk a minute about zeros of the graph. So zero. Zeros of a polynomial, which sometimes are, and actually are found the same way as roots or solutions. Your book loves using different terminology. So if you see roots or solutions, realize they're found the same way as zeros. But what are zeros? Well, zeros are, let's go by the definition. Oh yeah. They're x values which make f of x equal to 0. They're x values which make f of x equal to 0. And I know what you're thinking. You're thinking, hey, that looks really familiar. Isn't that just x-intercepts? And for now, you're right, okay? And I'm going to put that in parentheses. Found exactly the same as x-intercepts, okay? Remember an x value, look, this is just a fancy way to say y, right? So when y equals 0, the x value for where y equals 0 turns out to be just an x-intercept, okay? But the difference is that a 0 can be imaginary, okay? A 0, a root, or a solution can be imaginary. So when we have a real 0 or a real root or solution, it turns out to look just like an x-intercept on a graph, okay? But, excuse me, and like 3, 4, I believe, is when we get to there, maybe 3, 3. We'll wind up with non-real zeros. You won't be able to see them on the graph, but you will be able to find them the exact same way as finding x-intercepts, okay? So that's just the definition, and we're going to use this a lot, okay? You'll hear me say the word 0 now a lot throughout the rest of the semester, and really it's just x values that make f of x equal to 0. And we don't have to write these as coordinates, okay? They're just solutions, like x equals 5, x equals 2, and so on, okay? So we're going to do a very, very basic example of finding zeros for this next. I'm stealing this straight from the book. It's on page, like the bottom of page 352. F of x equals x cubed plus 3x squared minus x minus 3. And the question states find all zeros. Now, just for fun, I'm going to do the in behavior of this one. I know the book's not doing this, but it's just because I want to, okay? Because we went over that just a second ago. So in behavior of this, now look, our leading term is x cubed. So that means the degree is 3, and the leading coefficient is 1. So degree, that means odd, right? And positive. So that tells me the in behavior. Since it's positive, I know it's going to go up and to the right. And because it's odd, it's going to be opposite. So it's going to go down and to the left. So this is my in behavior for this graph. And I haven't graphed it, and I know the in behavior. Kind of cool. I know. Okay. B, let's find all the zeros now. Okay. So to find all the zeros, now remember, it's where f of x equals 0. So we have to set this entire polynomial equal to 0. So we've set this entire polynomial equal to 0. And notice, if it was just 3x squared minus x minus 3 equals 0, we could solve that no problem. That was a nice quadratic. We could do the quadratic formula, maybe it factors, who knows. But it's not. It's a third degree polynomial, okay? It is not a quadratic. So we're going to have to use different techniques to solve this one. Okay. I'm going to factor it completely. And I'll tell you in this section, I'm going to write this on the side. In 3.2, you can factor completely. When you come across a polynomial, you have to find the zeros for. And it's because your book's kind of spoon feeding it to you, which is a good thing. Okay. Baby steps. We're doing baby steps. And Dr. Blitzer, he really does believe in baby steps now that I'm kind of thinking about his book compared to other books. We're doing baby steps. And the first baby step is to see if we can factor it. If we can factor it, it's a lot easier to solve for. So let's see if we can factor this. Now look, we've got an x cubed plus 3x minus 3. If I want to factor this for all the brownie points in this class, what would we have to do to factor this? You can type it in the chat and you will receive all of my brownie points that mean nothing but respect from this side of the Zoom session. If I wanted to factor this, what would I have to do? What's it called? Oh no, is no one going to attempt to tell me? Oh no, you guys are going to fail all the brownie points. You're not going to get the brownie point. Look, guys, what was it? I think I had all three of you in the Dev 2 class. If I had 4 terms, how would I factor 4 terms if it's factorable? What was that called? We spent like a whole section talking about it. If you want to unmute yourself and yell it real loud, you can too. Oh, you're hurting me on this side. You hurt me. You can't remember what this is called. I'm being dramatic, which is what my wife tells me is a trait of mine. Okay. Again, it's called factor by grouping, right? Factor by grouping. If we had 4 terms, we're going to do factor by grouping. And remember, factor by grouping, you set the first 2 together, and then you set the last 2 together. And hopefully all 3 of you and everyone watching at home is going, oh yeah, I remember that. Oh, I can't believe I didn't think of that. So with factor by grouping, remember we group them together. That's a 2. Say what factors out of this first set? Oh, x squared. The second set, and then we'd have x plus 3 left over. Second set's got to match, right? So we've got to factor out a -1. We'd have x plus 3. And notice they match. So I can factor it out. And I'm left with what's left over. If you've never seen this before, or if you need a refresher, again, just get on the YouTube and put in factor polynomials by grouping. It'll pop up. Now notice this last term, x squared minus 1, it factors as well. Now it's a quadratic, which is nice. It's kind of our safety zone. If I wanted to solve this one out, I could pretty easy. But it factors its difference of squares. It's x minus 1 times x plus 1. Okay? Now notice there's some neat stuff going on here. We had a degree of 3 that we started with. Okay? I'm going to slow down right here and kind of talk about what's going on and what's neat. We had a degree of 3. And when we factored it completely, which all of them in 3.2 will factor completely. When we had a degree of 3, when we factored it, we had 3 factors with x. Kind of cool. Okay. Now, when we set each of these factors to 0, now I'm going to kind of finish this over here. I'm going to set each one of these factors equal to 0. So x plus 3 equals 0. Now, notice if x plus 3 is the factor, when I solve it, x equals -3 is the 0. Okay? So if x plus 3 is the factor, x equals -3 is the 0. So now, then the other one was what? X minus 1? I'll do that. X minus 1 equals 0. So x equals 1 is the actual 0. And then x plus 1 equals 0. So x equals -1. Okay? So look, this is not a coincidence. We have a degree of 3. We have 3 factors, and we have 3 solutions. Okay? Now, you might have repeated solutions, so it might not look like you have three. We'll get to an example like that here in a little while, but you do have three. So these will all match. The degree, the number of factors, and the number of zeros will all match. Okay, kind of neat. You don't have to tell me. I know. But let's also bring in, now your book doesn't do this. Well, actually, it does. It graphs this, and let's show what we know. This is called a rough sketch. We're going to make a rough sketch without popping it in a calculator. You're more than welcome to throw this in a calculator if you want to, though. But without dropping it in a calculator, let's kind of make a rough sketch of what we know. Sorry for the tilt. It's Monday. So 1, 2, 3. I know, remember, if it's a real zero, what that really means is it's an x-intercept. So I've got an x-intercept at -3, an x-intercept at 1, or -1, and an x-intercept at +1. So I have those three x-intercepts. That's with another color. I also know the end behavior. The end behavior goes down and to the left and up and to the right. So look, let's see what that actually means about these zeros. What that means is all the way to the left, this leftmost zero, I have to go down, okay? I have to go down. I can't go up because my end behavior is down. And I know I don't go back down because there's not another zero. It doesn't cross again, okay? And then all the way to the right, I know that this thing is up and to the right, okay? And just to make a quick sketch now, again, look, what's nice, if it's in this term, not in factored form, it's in this like term form, that constant is your y-intercept. So -3. So we get something that looks like this. It's not perfect. If you graph in your calculator, you can tell me, hey, that's not what the calculator looks like. But what matters is the end behavior is correct and where we cross the x and the y-intercept is correct, okay? Kind of tying it all together with a graph at the end is always kind of nice, okay? And I'll tell you, when we start solving these, a lot of times I just start with a graph. That's more for 3.3 and 3.4, but I'll start with a graph and just pull information off of it. It's nice to do that. But for now, we've got to get the basics before we can get to there, okay? Okay, this is a good spot to stop and ask you guys if you have any questions. Other than, I think I need to see another example, Mr. Shirley. Okay, let's do one now that's in that factored form. We're going to do the same thing. We'll see why it's nice when it's in factored form, okay? We'll see why it's nice when it's in factored form. Let's say we've got h of x. I thought your book brought up. Yeah, okay, good. H of x equals, and let's do something in factored form. Let's say x minus 3 squared times x plus 1, okay? X minus 3 squared times x plus 1. Now, I'm going to do the end behavior first just because I want to. End behavior, I think it's going to be the same as the last one. I need to do another example soon. But anyway, in behavior, we get x minus 3 and x. Now remember, that means there's two x's and then an x, right? So it's going to be x times x times x. So the leading term is actually just x cubed. So that means the degree is 3, it's odd. And the leading coefficient is 1, which is positive. It's the exact same as the last example. So therefore, the end behavior, because it's positive, it goes up and to the right. And because it's odd, it's going to go down and to the left. Excuse me. So let's find the zeros now. And look, when you're given a factored form and I ask you to find zeros, you need to go, oh my God, thank you, Mr. Shirley. Send me a thank you note. Thank you, Mr. Shirley, for putting that on test. This is the easiest question. Because if you set this equal to 0, that's how we find the zeros. We set the whole polynomial equal to 0. It's already factored for us. Now notice, I'm going to write this out to show you we do have 3 factors. Right? We have 3 factors. That one we just have twice. So we write it in this nice kind of condensed form. but we have x minus 3, and x plus 1. Our degree was 3. That's not a coincidence. And guess what? We're going to have 3 zeros. X equals 3, x equals 3, and x equals -1. Remember, if you set this equal to 0, you wind up with -1. This one equal to 0, you get 3, and this one you get a positive 3. Now notice this one happens twice. That means it has a multiplicity of 2. So I'm going to park it right here for a second. So I would write this in this manner. I think your book kind of writes it like this. X equals 3 has a multiplicity. It's not just a bad 90s movie with Michael Keaton. If anybody gets that reference, you get brownie points as well. Has a multiplicity of 2. Now, -1 has a multiplicity. It's just 1 because it only happens once. So if you want to write that, you're more than welcome to. X equals -1 has a, now for multiplicity, we can just use a capital M as a multiplicity of 1 because it only happens one time. But something neat happens when we have even multiplicities like 2, 4, 6, 8. And I'm going to show you on the graph what happens. Which one has the multiplicity? Okay, the 3. So we've got -1, 1, 2, 3. Oh, hey, if you want to get the y-intercept, you just have to multiply the constants together. -3 times -3 times 1. So just a quick trick on that one. So -3 times -3 times 1, that's a +9. So I know it's just way up here somewhere. But let's graph this one. So we're at -1 and we're at +3. And I know the end behavior tells me that this is going to go down and that this is going to go up, right? Okay, but now look, this doesn't make sense like the last one. You know, in the last one, this went down and it went back through and then back down. But it's got to go down over here and up. So like what that means is it actually bounces. The multiplicity, if it's even so it's even at x equals 3 here, it's going to bounce off this x-axis. Now, your book uses the terminology. Let me get this right. Is it turn around or something? Hold on. Touches. Yeah, it uses the word touches. It touches the x-axis. Boom. And it comes right now. Remember, the y-intercept was like way up here somewhere. So we'll do something like that. So it looks something like that. So because x has an even multiplicity, it bounces off the x-axis. Now, because it had an odd multiplicity at -1, it goes through the x-axis, okay? So it's going to bounce because of the even, and it's going to go through because of the odd. Pretty neat. That's the multiplicity. Now, if you want to read about that a little more, it's on page 354 in your book, okay? It's on page 354, which is kind of neat. Okay? Questions, comments, concerns? Okay, let's look at another one that's not in factored form. So, but remember, like going back and looking at this for a minute, notice when we set this equal to 0, oh man, it was like super easy because it was already factored. Boom, boom, boom. We had the 3 zeros real quick, as compared to, the last example where we had the non-factored form. You had to factor it first and then find the zeros, right? So let's look at something back in this non-factored form. I'm going to get it factored for this question. So again, I'm stealing this one straight from the book. This is on page 353 because I think this is a good challenging example. -4x cubed, or I'm sorry, -4x to the 4th. I said that wrong. -x to the 4th. That's what I was going for. Plus 4x cubed. There's the 4x cubed. Minus 4x squared. So first off, let's do end behavior. It's different. Okay, end behavior. Now notice the leading term here is negative x to the fourth. So look, I'm going to go right into the end behavior. Because we have a leading coefficient that's negative, I know that this is going to go down and to the right. Okay? I've got a degree that's even, so it has to be the same on the other side. Okay? It has to be the exact same. So B, let's find the zeros. Now, I need to do one. I'll do one. On the next one, I'll kind of show you if it says like find the roots or find the solutions, how it's written a little differently. We'll do that one on the next one. Well, let's find the zero. So I've got negative x to the fourth. Remember, we've got to set this whole polynomial equal to 0. And I'm going to factor it. Now look, to factor this one, I've got a negative out front. So I'm probably going to factor a negative out. But look, notice the first step in any factoring is to see if we can factor out a GCF. And we have at least an x squared in all of these terms. And because I want this first term to be a positive, I'm going to factor out a negative x squared. Okay? And when I do that, this first term becomes just a positive x squared, right? I factor the negative out. Second term changes sign, so it's going to be negative 4. I factor an x squared, leaves me with an x. And lastly, I factored all the x's out, but this becomes a 4. Okay? So I've got negative x squared. And now I've got to factor this quadratic, which is not too bad because it's an x squared by itself, so I can write it in parentheses. I can just pop it in there. Well, what two numbers multiply to give me 4 and add to give me negative 4? Hopefully you're yelling, -2, -2, because you're right. Multiply to give me 4, adds to give me negative 4. Hey, notice these are the same. Oh, this is kind of cool. Okay, look. We've got negative x squared times x minus 2 squared. So in factored form, if we wanted to write it shorthand, we have two sets of multiplicities of 2, right? Kind of cool. Like if this is how we'd write it shorthand, long factored form, it would be negative x times x minus 2 times x minus 2. You don't have to write this out if you don't want to, okay? But realize from the x's, you would get x equals 0 as the actual 0, okay? And you can write it twice if you want. The x minus 2, you would just get x equals 2. There's two distinct zeros, 0 and 2, okay? But both of them have a multiplicity of 2 because, look, there's two factors that produce x equals 0, and there's two factors here that produce x equals 2. So they both have a multiplicity of 0. That tells me when I graph this, we'll do part C graph. When I graph this, I know that I'm going to bounce or touch, as the book says, at x equals 0 and x equals 2. Let's see what that looks like. Okay. Now, my x-intercepts are the zeros, right? So x equals 0 is right here. Let's do x equals 2 right here. I know my end behavior is down and down. So from these two zeros, I know I've got to go down and to the left and down and to the right. Okay? And notice I don't have a constant out here. That means that the y-intercept is 0. Okay? But what's neat is my multiplicity on both of these is even. Okay? I've got an even on both of these for their multiplicity. So that means on both of these, they bounce. This is going to make like an M. Kind of cool. Made an M. M for might be understanding this at this point. Okay. Questions. I'm going to give you guys one here in a minute. And I want you to do the A, B, and C. And really, I don't want you to use the calculator unless you just need some kind of basic math. I want you to not use the calculator. So then when we get to using the calculator, it won't be like a crutch. It'll be just actually to make the question go quicker. Okay. And you'll thank me for that when we get to 3.4. Now you probably won't thank me for it, but you should thank me for it. Questions about this one before I go on and just get, I'm going to find an example from the book and ask you to solve it. Okay, I think your book goes over this. Maybe, maybe not. Well, it starts, why does your book, hold on. Okay, here we go. This is number, I'll do an even one. Number 30. Yeah, we could do number 30. Why not? It looks a little different. So this is number 30. I want you to try this one. Number 30, it's on page 361. It says f of x equals x cubed plus 4x squared plus 4x. And the question says, find the zeros for each polynomial function and give the multiplicity for each zero. State whether the graph crosses the x-axis or touches. So I'm going to do this a little differently. I'm going to do, first, let's do in behavior. Make sure we've got that down. And then I want you to find the zeros. And without using your calculator, I want you to graph it. I'm going to do C over here. Okay, so try those three. I'm going to give you a little bit of time. I want you to try those three. Or try this one. Answer those three questions, I should say. Okay, keep working. If you're working, I'm going to do the in behavior first. Look, I'm going to be a little lazy here. I know it's positive leading coefficients, so that means I'm going to go up. Odd degree, so that means I'm going to go down and to the left. Okay, and I'm going to tell you, of all the hard stuff we're going to do over these next few sections, I get the, oh, let me start recording again. Of all the hard stuff that we kind of go over the next few sections, in behavior tends to be something students kind of just get backwards. I am getting a phone call in my office. Hold on. There's no reason I should be getting, okay, it bounced around. That's weird. Anyway, so just realize that we get this kind of backwards, so be careful. Positive means we go up. Odd means it's the opposite. So now let's find the zero. So I'm going to set this polynomial equal to 0. Now I told you I was going to do one that for a solution or a root. I'm going to have to do that one next. Okay, because this is still just finding zeros. So x cubed plus x squared plus 4x equals 0. So notice on all three of these I've got an x. I have to factor that out first. Okay. And then, oh, this factors again, it's a positive 2 now though, right? Positive 2 and positive 2. Multiplies to give me 4, adds to give me the 4, adds to give me the 4. So that means my zeros are actually x equals 0 from there, and then x equals -2 and x equals -2. So look, this is a multiplicity of 1, if you want to kind of box that one in, because that's your book asks for that, right? State the 0 and then its multiplicity. So that means I'm going to go through right there. Now x equals -2 though, I'm only going to box it in once. It has a multiplicity of 2 because it happens twice, right? That means I'm going to bounce. So if I do a quick sketch here, -2. I'm at 0 and I'm at -2, right? I'm using my red pen again. Just it pops on paper. It really looks good, snazzy. Okay. 0. Well, actually, the end behavior tells me I'm going to go down here. I'm going to go up here. But at -2, I'm going to bounce. I use in the past, I would do a little R. Kelly keys to ignition for this. And then R. Kelly got really weird. And I don't feel like it's appropriate to use R. Kelly references in class anymore if you've seen anything about R. Kelly in the past 3 or 4 years. So, but I would make this bounce, bounce, bounce reference. And some students would get it, some wouldn't. But now R. Kelly's just a creep. Actually, I guess it was a creep back then too. We just didn't know it. Okay. Rant over about R. Kelly in college algebra at 7 or at 8 a.m. Okay. Any questions? Did you guys get this? Kind of letting you do it on your own now. Hoping you grasp it. Okay. Let me give you one where I'm, it might just wind up being the next section. It must be. The next section is when they go over kind of the solutions or the roots. And I'll have to get to that then. Okay, let's do another one. I'm going to steal one from your book again. Let's steal a factored one. It's kind of easier. Let's do 58. And 58, they ask for a lot of different things on 58. It said, A, use the leading coefficient test to determine the graph's end behavior. Actually, let's just try 58 and start working through it. F of x equals x cubed, x plus 2 squared, and x plus 1. Okay, so A says end behavior. Okay, sweet. We've been doing that already. Now, end behavior, though, now I got to think about this one. So x cubed times x squared, right? Because we have to do it twice, and then times x. So the leading term would be x to the 1, 2, 3, 4, 5, 6. X to the 6th power. That would be the leading term for this factor. So that my end behavior then, we got a positive leading coefficient. It's going to go up. It's even, so it's going to be the same on both sides, even degree. Positive leading coefficient of 1, that tells me it goes up. Even degree, so it's going to be the same on the other side, right? Great. So part B says find the x-intercept. State whether the graph crosses the x-axis or touches the x-axis and turns around. Now look, I am going to be a math snob when it comes to x-intercepts. If it asks you for x-intercepts, that's a coordinate, not a solution. So we're going to write x-intercepts as a coordinate. But since it's in this factor form, it's kind of easy. So we'd have x cubed times x plus 2 squared times x plus 1 equals 0. And notice, look, x cubed equals 0. That would just be x equals 0. Oop, that's not going to be my solution though. X plus 2 equals 0. That means it's x equals -2. And x plus 1, that's x equals -1. Now look, I know this is a me thing, but because it's asking for intercepts and not zeros, we need to write these as a coordinate. This would be the coordinate form for the x-intercepts. Now let's go back though. Look, x equals 0 happened 3 times. So its multiplicity is 3. That means it's going to go through. Box that all in together. X equals -2 happens twice. That means we're going to bounce. So it's got a multiplicity of 2. We're going to bounce here. Okay. And then x plus 1 happens once, right? So its multiplicity is 1, so we're going to go through. Boom. I think that's B. Yeah, stay whether it touches or turns around. Oh, bounces, so turns around. Your book uses the terminology turns around. So C, find the y-intercept. Now remember, I told you y-intercept is kind of nice because you multiply these out. But if we have an x value by itself, look, remember, if I want to find the y-intercept, I set x equal to 0, okay? You set x equal to 0. This is the formulaic way of doing this, f of 0. So you get 0 cubed times 0 plus 2 squared times 0 plus 1. Well, 0 times 2 squared, so that's 4, times 1. Well, 0 times anything is just 0. Now, remember I told you, you just have to multiply the constants? Well, it's because this x cube's by itself. Because there's an x value out there, it winds up being 0. So if you want to do this the formulaic way, that would probably make the most sense. For y-intercepts, remember, we just plug in x equals 0. So for this example, we wind up with 0, 0. Okay, that's our y-intercept. A, B, C, D. Determine whether the graph has y-axis symmetry or so. Oh man, symmetry. We haven't done that in forever. Now remember, for symmetry, you plug in negative x to see if you get back the same thing. You know what? I'm not worried about this. I'm just going to look at the graph to determine if we have symmetry. So I'm going to skip over it. I'm not a fan. Look, there's some mathematicians that feel symmetry is the most important part of mathematics or algebra. I'm not one of those people, okay? I'll tell you, not going to be on the test, okay? Symmetry is not going to be on the test. All this stuff leading up to it is going to be on the test, okay? Then part E, if necessary, find a few extra points, and we're going to graph it. So we're just going to graph it. Okay, we got 0, -2, and -1. So -2. Use my red pen again. -2, -1, and 0. The end behavior is up and up. Right? Excuse me. Now, it goes through, 0 and 1. It bounces at -2. Okay, so it's going to bounce here, but then it's going to go through at -1 and through at 0. Okay, so it's going to bounce here, bouncing at -2, but then it's going to go through the other two. Something like this. I know in your calculator it's not going to look like that. It's going to be a lot more drastic because we have a degree of 6. Degree of 6 means we have like just really, like crazy steep lines. But I can tell you this does not have symmetry. None. I go back to here. Because it's not y-axis symmetric. Remember, you had to flip it once. And it's definitely not origin symmetric where you flip it twice, where like it had the same symmetry, kind of catty corner. Oh my gosh. Regions. They're not called regions, but anyway, yeah, it doesn't have x-axis it doesn't have origin symmetry or y-axis symmetry, so there's none here. Okay, this is a good example that incorporates everything we've gone over today, really. And notice the graph is smooth and continuous, right? It goes on forever. Pretty cool, I know. You don't have to tell me. Okay, now your book goes over something called intermediate value theorem. I don't go over that in this class. If you want to look at it, you're more than welcome to. But it's not going to be on the test or the final. And I don't think it's that important for college algebra. I'll tell you, if you go into a calculus class, it'll get brought back up, okay? And they'll talk about it more in context with calculus. And that was one of the reasons why I don't go over it, because a calculus class really goes over it in the terms of calculus and not really in the terms of algebra. Okay, so let's look at homework. So page 360. Let's do 1 through 31, and then we're going to jump over the intermediate value questions. Do 41 through 63. All these are going to be odd, guys. And then 73 and 75. So all these are going to be hard. If you want to hit like every other question in this stretch, 41 through 63, you'll see 1 through 31 won't take long. Those don't take long at all. They shouldn't, actually. The first part anyway shouldn't take long. But if you get that stretch of like the same kind of questions, you can do every other odd just to make sure that you know what's going on. Okay. Okay. Let me stop that. I'm going to pause it here. Do you guys have any questions before I turn this off? Remember, tomorrow, if you're watching this later, this is not true, but tomorrow is election day. Go vote. Your vote matters. Please go do that. Yep. And what that also means is Wednesday, the election will be over. It might not be over because they're still counting ballots, but the ability to vote will be over, which is nice because then we won't have to hear about the election anymore until they, hopefully not. Oh God, I hope this isn't like a 2000 thing. Okay. Any questions, comments, or concerns before I get off here? Yeah, you are exactly right. It'll be nice when it's over. That's I feel like that's just the slogan for every election. Hey, it'll be nice when it's over. Okay, I'll see you guys, and I'll see you tomorrow morning. We'll go on 3.3. 3.3 kind of takes a left-hand turn, and then in 3.4 we're kind of back to the finding zero stuff. So kind of neat. I will see you all later.